Hello, welcome to part 3 of this talk. So far, in part 1, I've reviewed what's special about general relativity, following a Pooley 2013 paper. The purpose of this section was to motivate how general covariance is a support for diffeomorphism invariance and background independence. In particular, it helps us clarify questions about symmetries, and it helps us identify background structure. In the second portion of the talk, I talked about the Nyquist-Shannon sampling theory and how this works. We talked about band-limited functions, uniform sampling, and non-uniform sampling, and how all of this works in one dimension and in higher dimensions as well. In this portion of the talk, I will combine those two into a discrete notion of general covariance. Just as the continuum general covariance supported diffeomorphism invariance and background independence, so too, or at least it's my hope, that this discrete general covariance will allow us to make clarified statements about symmetries and about background structure in discrete theories. So let's see about that. Recall the proposed analogy that I've been discussing. We have now lattice structures being analogous to coordinate systems. We have the Nyquist-Shannon resampling analogous to changing coordinates. And we have band-limited formulation analogous to a generally covariant formulation. Having seen part 2, maybe you have a bit of an idea about how this will work. So far, what I've done in section 2 was talk about band-limited functions and then induce discrete lattice representations from it. We can also start with a discrete representation and build it up from it, a band-limited function. Which of these two perspectives, band-limited going to discrete or discrete going to band-limited, we prefer is, at this point to me, a matter of taste. I think it has interesting philosophical implications whether we view the situation one way or the other, but let's hold that off until the end. Once we have this band-limited formulation, we can resample it and get other discrete representations. So this motion from discrete to band-limited back to discrete, this is sort of what I mean by Nyquist-Shannon resampling. These two motions together give us transformations between different discrete representations of our theory. So this is what I mean by Nyquist-Shannon resampling and how it's analogous to coordinate change. In the analogy, these lattice representations are like coordinate systems, and we're free to change between them by a process like Nyquist-Shannon resampling. Of course, then, just as over here, there exists a coordinate independent formulation, general covariance. Here, there exists a lattice structure independent formulation, which is band-limited formulation. So this analogy, if it works out, sort of implies that the band-limited formulation is the correct one, in a sense, in that it has removed this representational artifice from our theory and is therefore, the cleanest and most straightforward presentation of it. So if this analogy holds as I've been talking about it, the band-limited formulation is sort of the central one or the core one, and we induce different lattice representations on it by a process like the sampling that I talked about in section 2. But you don't have to view it that way. I mean, we'll get to it. I'm getting ahead of myself here. Okay, so moreover, what we'll do is we'll add in dynamics to this situation. And using this, once we have some dynamical equations, then we can make concrete questions about symmetries in these discrete theories and about the background independence in this discrete context. As I've said multiple times, general covariance is a gateway in for diffeomorphism invariance and background independence. As a first example, let's consider this 1D nearest neighbor heat equation. We have the time derivative of some value here, psi n of t, being related in some way to these other values of psi n, still at t, but now at different indices here, n plus 1, n minus 1. Here's a note here. There's no manifold in this formulation of the theory as I've currently written it. These are just discrete points, not even discrete points. These are just values which exist over time. I'm not saying anything about how they're related in space. There is some dimensionful constant here, A. A has units of length. So what does that mean in a discrete theory? I don't know. Anyway, we just have these discrete values related to each other over time. Equivalently, let me reformulate this and put all of these values together into a vector here, psi minus 1, psi 0, psi 1. off to infinity in both directions. This vector, I can talk about how it evolves, and it evolves in this case by a linear equation, alpha over a squared. This delta is now an operator which acts on this vector, and delta is the nearest neighbor approximation to the second derivative that's sort of given up here. This is supposed to be a model of the heat equation, so we have a time derivative proportional to a second derivative in space, sort of. This is the equation down here written in terms of this vector. And so this delta is a tridiagonal matrix with -2 down the diagonal and 1 off either side. That's what delta 1 is. So what we can do, and at this point, I have a sneaky note here. I'm sneaking a manifold in somehow. There's lots of different ways to do this part of the talk, and I'm just picking one in a way that's sort of compatible with the regularity relationism. But again, I'll come back to this later. Let's just go ahead with the talk now. At each time, we can choose these discrete values, take them, and imagine them as samples drawn from some band-limited function psi b. So this psi b at the moment is just imaginary, but we'll see that we have reason to take it more seriously later. So suppose there is some psi b, and suppose there are some, that the index n is actually related to a position in space, xn, equaling na, where a here is the same constant here that appeared in the bottom of our formula. Let's just suppose that this is the case, right? Just as a sort of imaginary representational thing. Psi b evaluated at these points xn will give back this psi n. Okay, so it matches at all these discrete time points, but we've said nothing about how it behaves between them. But recalling our band-limited discussion from earlier, there's only one band-limited function which matches those discrete values. We can use these values to construct that unique band-limited function in this way. We take these discrete values, multiply them by sign functions, shifted, sinc functions, sorry, and add them all up, and this will give us a band-limited function. And it is, in fact, the unique band-limited function which satisfies equation 21, which does match these discrete values at these locations. So there's only one way to do that, and so just imagining that there is something which matches in some places, we find that, oh, well, we know what psi b does everywhere, in both space and time. So in this way, we've moved the state of the world at each time over into the lattice description. What we can also do now here is move the dynamics across into this band-limited setting. Here we have the band-limited function here. It will obey some sort of a differential equation, taking its derivative in time and applying that onto these discrete values here, psi n. We can use equation 19 to do some long process of rewriting, which I've skipped here, to give this formula here. And so it turns out psi b, this band-limited thing, which we are just imagining here at the moment, it obeys some sort of differential equation, which is very nice. Alpha divided by a squared, hyperbolic cosine of a derivative, minus 1 divided by 1/2 applied to psi b. Now this is a very complicated cosh term, which has the cosine, hyperbolic cosine of a derivative. What exactly does that mean? What it turns out to be is it's the continuum analog of this delta 1 squared. Recall what delta 1 squared did. It sort of moves you forward one step here. It also moves you backwards one step here. And it combines those with translating an amount of 0. So translation here, f of x plus a, translating by one lattice site, is to multiply the function f by this exponential of the derivative. If you expand this out in the Taylor series, you find that this formula is in fact true. And so what this cosh does is it translates one unit to the right in a, one unit to the left in a, right? It's those two, and then subtract that from not translating the identity function here. And so this is the continuous version of delta 1 squared. It is some differential operator. Now, the series here determines this hyperbolic cosine. It has infinitely many terms in it. So there's infinitely high numbers of derivatives here. So in that sense, this is not a local operator. It's in fact a non-local operator. But more about that later. If you take this cosh expression and expand it as a series in A, you find it's the derivative squared plus some corrections at a higher order, a squared derivative 4. And so if A is small in some sense, exactly what sense needs to be clarified, but if A is small in some sense, you get back the second derivative here, which does make our theory look like the heat equation. Derivative here equals second derivative plus some corrections times this. So you get something like the heat equation, which is good because we're supposed to get back the heat equation in the continuum limit if we send A to 0, which it does look like that's what happens here. So that all checks out. So that's the theory which I'm going to call H1. This is its discrete representation, and this is its continuous representation, or its band-limited representation, I should say. H2, let's consider another theory, where we have the derivative of this vector equaling this other operator applied to the vector, where delta 2 is the next to nearest neighbor approximation for the second derivative. Running through the same process, you'll find that the differential equation with psi b of a's in this case is different from the first one. This is different dynamics. The sites relate to each other in different ways. So the derivative here, it turns out, is this other cosh-like expression. Here, this cosh of 2a is translating 2 sites to the left and 2 sites to the right. So in total, 5 lattice sites are involved in this. Your 2 left neighbors, your 2 right neighbors, and yourself. As a third theory, consider this one. This dB, it is the limit of nearest neighbor approximations as n goes to infinity. So it's an infinite range derivative approximation. You tell me the values of the lattice everywhere in space, and I will return to you an approximation of the derivative locally at each site. That's sort of the thing that this does. More to say about that later. It's a very interesting function, this dB. Anyway, the the band-limited version of H3 is just this thing which looks remarkably like the heat equation. Exactly. The derivative in time equals alpha derivative in space. So we have these 3 different theories. And note how this one is local, or the most local in the terms of the lattice, but it's non-local in terms of the band-limited function. This one is intermediately local in terms of the lattice. It now needs 2 sites for the left and right. And if you expand out this, you find that it is, as a series in A, you find it's very similar to this. It's delta x squared plus, in the second case, it's A4 derivative 6 here. So this thing is a closer approximation to the second derivative, but it has to use more lattice sites to do so. Here we have an exact sort of representation of the derivative, but it has to use an infinite number of lattice sites. And now this operator is local in the band-limited case, whereas this one is non-local in the lattice case, right? So we have this trade-off between locality in the lattice description and locality in the band-limited description. I'm not going to say much more about that, but very interesting questions, which I'll pose at the end of the talk about that. In each of these 3 cases, the eigensolutions to these equations are plane waves. And these plane waves decay exponentially in time. If you're familiar with the heat equation, this is sort of what you should expect. The heat decay rate, the solutions to the heat equation, are plane waves, like just imagine a sine wave. And then the amplitude of that sine wave decays exponentially in time. And the rate of that decay depends on the wave number. So you have this heat decay rate versus wave number. And in the continuum case, it's quadratic, just like H3 here. Except in the continuum case, it goes out to infinity, off to either side. Here, the solutions only work with k less than k. Because of an aliasing effect, any frequencies you try and define higher than this will be identified back with these lower frequencies. So these lattice theories, they do not support at all frequencies higher than this bandwidth. So you have the these curves really do truncate here. Like the continuum curve continues on, but these 3 curves all truncate here. So what do we have? We have H3 matches the continuum curve for all k less than k. We have these 2 departing from it at some point, but matching qualitatively around here in the IR, around for low wave numbers. What this shows us is that there's no need for the lattice theory to have different dynamics than the continuum theory. In particular, if we start with the continuum theory and then introduce a lattice, you may ask, well, what effect does that lattice have on the dynamics? It doesn't necessarily have any effect at all, besides, of course, cutting out frequencies above the bandwidth of that lattice. But up below that bandwidth, there doesn't have to be any dynamical effect at all. Okay, continuing on. We have here a space-time diagram of a solution for the heat equation, which, as I just mentioned, is a plane wave here in space, which decays its amplitude exponentially over time. So we can plot the discrete values psi n of t, which are indicated by these dashed black lines, and we can plot the band-limited function psi b of x and t here in the space-time diagram. We can then pick new sample points at each time. This is what I'm talking about when I say Nyquist-Shannon resampling. In particular, we could pick these red points here, which move about as they do, sort of arbitrarily, on the lattice. Now here, coincidentally, they all stay equally spaced. They all stay uniform as they move forward in time, but they don't have to, as long as they are sufficiently dense, whatever that means. Sufficiently dense is a technical term, which is hiding quite a lot of information. You should know. Anyway, as long as they remain sufficiently dense, it will be fine. These new sample values, the values of the function at the red points, will obey a different equation than the dashed black points do. But nonetheless, they're completely sufficient to represent the dynamics. Recall earlier when we had the Klein-Gordon equation and we wrote it in different coordinates. We found that the new field obeyed a new equation, but it's still a representation of exactly the same thing. It's just a change of representation. What about this resampling here, where we've just taken the points and moved them by a static amount, say a shift of a bit in the right direction? Do the shifted red sample values obey the same equation as the original dashed sample points do? It turns out that yes, in fact, they do. So these equations, these red values, which are different from the black values, obey the same equation exactly. What this indicates is that there's no reason that a lattice theory can't have a continuous symmetry. A lattice theory having a continuous symmetry, that's quite odd. You may think that I'm saying here that this band-limited differential equation, the differential equation obeyed by the band-limited function, has a continuous translation symmetry, where this solution is mapped to this thing, which is also a solution, and shifted by epsilon. Indeed, H1 does have that symmetry, but I'm also saying more than that. What I'm saying is that this equation H1 here, which relates these discrete values together, also has a continuous translation symmetry, even when there's no manifold underlying these lattice points. The symmetries of a theory should not depend on how we represent that theory. These are just different representations of the same thing. That's what my analogy is suggesting. And as such, they should have the same symmetries. If you take this band-limited function here and apply this transformation, and then resample it on the same lattice as before, you'll find that you'll have a transformation which is induced in this discrete landscape, right? And so we can, from this transformation, induce the transformation that goes on down here. What exactly does that mean? How does this discrete equation have a continuous translation symmetry? Concretely, and this gets a bit technical, don't worry if it doesn't quite make sense, there's a representation of the translation group acting on the vector space Rz. We're using some representation theory here, some infinite dimensional representation theory, in fact. That is, what I mean by that is that there's a set of linear maps, T of epsilon, which maps these vectors onto themselves, which maps solutions to solutions of H1. If psi of t is a solution, then T epsilon of psi of t is a solution as well. And in particular, psi of 1 in this case is going to be translation by one lattice site, which is something we can definitely make sense of in terms of the lattice. But t is not only defined at integer values. At integer values of t, we have a subgroup here, which is discrete translation group, but we also have the continuous translation group. That is, like T of epsilon is defined at all values, and it obeys the translation group's group symmetries, right? So T of 1/2 times T of 1/2 is equal to T of 1, as is T of 1/4 times T of 3/2, T of 3/4, sorry. So this is a fine representation of the translation group, which here acts on this. And in the band-limited case, we can understand it as like a physical translation. But here it's something a little bit different. But there is still a continuous translation symmetry going on here. The situation is a little bit similar to what goes on with, say, the spin of an electron. Electrons, spin 1/2 objects in general, have a rotation symmetry in their internal space. They have rotation symmetry as they move their positions around, but they also have an internal rotation symmetry, right? And there's different representations of that rotation group. In particular, there's a two-dimensional representation which describes spin 1/2 systems. That rotation, though, it's not a physical rotation. The electron is not physically spinning. It's not a rotation in space which does that. There's another sort of thing which goes on inside the electron, which has the rotation symmetry group, but it's not a physical rotation. The same thing's going on here, that these are discrete values and they have something which is valued in the translation group, but which is not a physical translation. It has exactly the same group structure as that. Exactly the same as the spin of an electron. Let's do another example here, which I think shows the symmetry thing I'm talking about more clearly, and that's rotation invariance. Consider the initial condition for the 2D heat equation that I'm showing here on the left. This is the Bessel function that I talked about earlier. We can sample this initial condition and then evolve it via one of our discrete dynamical equations. And here are two that we might consider: H4, which is the nearest neighbor derivative in the x direction and the y direction, or alternatively H5, which is the infinite range derivative in the x direction and an infinite range derivative in the y direction. Evolving by these gives us different results. H4 and H5 are different equations. So evolving by H4 here and evolving by H5 yields different values. You start from the same values here and evolve them by these two different equations, find different values at the end of the day. We can then take these discrete representations and reconstruct the continuous, or the band-limited representation, I should say. And in this case, we find that the state is no longer rotation invariant, whereas in this case, it is rotation invariant. Putting those side by side, we have initial condition, initial sampling, the same at this point, evolved by H4 in this case, evolved by H5 in this case. And then when you do the reconstruction, you find that the rotation variance is broken here, whereas it's preserved here. And this indicates that H5 is a rotation invariant dynamics and H4 is not. We here arrive at a second lesson, that we can have rotation invariant dynamics described in terms of a squared lattice. This transformation from here to here is rotation invariant, and it's described on a square lattice. There we go. Here's another aside on representation theory. It's worth stressing here that there is a representation of the rotation group here acting on R2Z equals RZ cross RZ. I mentioned earlier how the spin rotation of an electron is a representation on R2, or actually, I think it's C2. Is it C2? Anyway, there's a two-dimensional representation, whether real or complex, of the rotation group that governs spin. Here's a different infinite dimensional representation of the rotation group, which is acting here. So this representation is a family of linear maps, R of theta, which maps R2Z to R2Z, which are 2D arrays. So it maps these 2D arrays to 2D arrays. And moreover, the group structure of R theta is exactly that of the rotation group. In particular, R of 2 pi will be the identity, and R of pi over 2 will be a quarter turn. And we can make sense of a quarter turn in our lattice. We just take all the values, rotate them by a quarter, and put them back down. But also, non-quarter rotations can also be made sense of. R pi over 4 times R pi over 4, there will be some representation of this, and those will multiply together to give R pi over 2. So there's a discrete representation of the rotation group going on behind the scenes. And what that means is that using this R2Z representation of the rotation group, we can judge the rotation invariance of states without talking about psi b. We don't have to talk about the band-limited landscape at all to make sense of this transformation. H4 is not rotation invariant, just because r of theta acting on it does not leave it the same. This state here, evolved by 5, is rotation invariant because it's invariant under the action of r of theta, which is that representation of the rotation group. So we don't need to talk about the manifold at all to do this. And again, these pictures are slightly misleading because I've drawn it here as if there's a manifold going over them and that these lattice points have definite locations, right? But you can think about H4 and H5 without referencing any sort of manifold at all. These are just discrete values, and they just have their values, and they associate with other places, and they evolve forward in time. And this state is rotation invariant, and this one is not, even if we don't think about the space underlying them, even if there is no space underlying them. Here's another example of the 2D heat equation. Start from this initial condition in either case. Now we have two different initial samplings. Here, this one on a hexagonal lattice, and here, this one on an irregular lattice. We evolved them both forward by H5. However, H5 ends up being represented in this lattice. And then we do the reconstruction here. And in both cases, we find that the end state is rotation invariant. And in fact, it's the same state. We just carried it out in different lattices. So we can have rotation invariant dynamics described on any kind of lattice. Hexagonal, irregular, whatever. Another last example of using these pictures. Here we have the initial state, which is rotation invariant, and then we do an initial sampling of it. And then we evolve by H4 in either case, which remember is not rotation invariant, and we get these states here at the end. And then band-limited reconstructions of them will yield these two states, which are identical to each other, but neither of which is rotation invariant. And what this shows us is lesson number 3. The fourfold symmetry of the H4 dynamics is just that. It's the symmetry of the dynamics. It has nothing to do with the dynamics being represented in terms of a square lattice. So the squareness of this lattice does not explain the fourfold symmetry of this, because we can do the exact same thing in this hexagonal setting. So the symmetry is of the dynamics. Really, all of these lattice points are representational structure, which doesn't explain symmetry. Okay, so let's work through that, not in pictures anymore, but in mathematics. The discrete 2D heat equation that I've been talking about, H5, is written down here. This psi represents a 2D array of values. And here we have this operator, which does the derivative in the x direction, and this one in the y direction. So here we have 31. This has a band-limited representation, which looks like this. The derivative in the time direction is proportional to the two space derivatives. All right. And so this hopefully isn't surprising, given what I've told you about dB squared. We can further reformulate this in a generally covariant way, just as we did before. So it's worthwhile looking at what's happening here. In the move from 31 to 32, we've gotten rid of the lattice structure, which we now regard as a representational artifact, and replaced it with coordinates here, psi b of t and x and y. But coordinates are themselves a representational artifact. We don't need them either. And so we then make the general covariant move to go to 33. And we reformulate this in a generally covariant way here. We have a manifold and some metrics and a derivative and a time-like vector field, just all as before. I discussed the heat equation in part 1. And the dPMs of this are given by the time derivative in the x, or the derivative in the t direction being proportional to the second derivative in space here. So compare this with the generally covariant continuum heat equation. Here's H5, just as from the last slide, and here's the continuum heat equation. And the only difference between these two is that in 34, psi b is band limited, whereas in 35, we have psi here, which is unrestricted. That's the only difference between these two. I asked the question earlier in part 2, what background structure do lattices introduce? In this case, it's nothing except a band limit on the field, the physical dynamical field here. If you place a band limit on it, that's all that you need to get this discrete system out of this continuous one. And moreover, since these dynamics preserve band limits, Remember I mentioned that sine waves evolve into exponentially decaying sine waves in the future. These dynamics preserve band limits, right? Band limited initial conditions evolve to band limited later conditions. So this ultimately amounts to just a restriction on the initial condition. All that you need to get from 35 to go to 34, if you place a restriction on the initial condition of psi b, that's all you need. Everything else follows from that. All the way back to here. This H5 is equivalent to this, well, they're at least equivalent mathematically. Philosophically, we have more questions. But at the level of mathematics and representations, all you need is to fix a band limit on the initial conditions, and then you get to H5. Let's consider also the discrete Klein-Gordon equation on a square lattice here. We have derivatives in time, here equaling derivatives in space minus a mass term. This has a band-limited representation of this kind. And note, we switched out lattice structure. A square lattice was assumed behind the scenes here. And we get this band-limited representation of the dynamics. We can further reformulate this in a generally covariant way, getting rid of the coordinates. Then we'll have a manifold, a fixed Lorentzian metric, and a field here, which is band-limited and obeys the Klein-Gordon equations here. Compare this with the continuum Klein-Gordon equation here. Here we have the exact same thing with the restriction that psi b is band limited in 39, whereas psi is unrestricted, phi is unrestricted in 40. It's the only difference. And again, the Klein-Gordon equation preserves band limits, so this ultimately just amounts to a restriction of the initial condition, again in this case. In the conclusions, I'll talk about a third case where you need slightly more than restricting the initial conditions. This initial condition thing, it just works out because the heat equation is linear, and so is the Klein-Gordon equation. It's linear in the dynamical fields. If it's nonlinear, some other things happen, but I will talk about that at the end. Okay, what does all this boil down to? The discrete Klein-Gordon equation, which I've written down here on a square lattice, has a full Poincare symmetry group. Now, it's a representation of the Poincare symmetry group, so it's not exactly what people maybe imagine when I say doing a Poincare transformation on a manifold. There is no manifold here, but this equation has the Poincare symmetry group. With one slight exception, which I'm not going to talk about too much. The value that the bandwidth has, you have to define a space-like hypersurface, a flat space-like hypersurface, in order to compute this bandwidth. And the value of that bandwidth depends on how you do the slicing. But other than that, this thing has a Poincare symmetry. This is the only thing which does vary with that symmetry. And that may not be too surprising. Like the material contents of the world, this psi, it has a minimum bandwidth in some frame. This is similar to the fact that the matter distribution in our universe, or at least in our observable universe, has a minimum velocity with respect to some frame. There is some frame which is co-moving with the universe, and that frame is special in some sense, but in other senses it's just contingent. It's just a matter of fact that, oh, the matter happens to be co-moving in this frame, and there you go. So this isn't too big of a concern about breaking the Poincare invariance of this theory. So here are my conclusions. What I've argued for so far is the analogy that coordinate systems are essentially equivalent to lattice structure, and the changing coordinates is equivalent to a Nyquist-Shannon resampling. We rearrange our lattice structures or pick new ones by doing this sort of resampling move. There is, of course, a coordinate-independent formulation on this side, which is the generally covariant formulation. And over here, there is a lattice structure-independent formulation, which is the band-limited formulation. Once you've done that, you can take your lattice theory, lattice in quotes, because these aren't really lattice theories, they're band-limited theories, which pick up a lattice-like representation in some cases. So once your lattice theory has a band-limited reformulation, you can run it through the left side of this as well, and get a generally covariant reformulation of that as well. So all of this move, what it does is it exposes background structure and it clarifies questions about symmetries. So what we've seen is that the lattice structure underlying a lattice theory has the same level of physical import that coordinates do. That is, none at all. So the first conclusion that we can draw from all of this is that introducing a lattice to a continuum theory does not need to distort the dynamics much, if at all. In the two examples we talked about, which were the heat equation and the Klein-Gordon equation, it can do as little as to restrict the allowed initial conditions. Now, as I mentioned earlier, this changes for nonlinear theories, which I can talk about in a second, but it mostly holds. So, in particular, the lattice theory doesn't need to cause a modified heat decay rate or modified dispersion relations in the Klein-Gordon expressions. I didn't talk about this, but normally if you put a quantum field on a lattice and go with a nearest neighbor approximation, you find a modified dispersion relation. You don't need to if you use these infinite range derivative approximations. Okay, the second point of the conclusions is that the lattice doesn't in any way restrict the symmetries that our theory can have. The symmetries of our dynamics is completely independent of the symmetries of a given lattice structure, which, given the analogy, this should make a lot of sense. The lattice is just a representational structure. There's no reason that we have to represent the dynamics in a way compatible with the symmetries of the dynamics. We can have Cartesian coordinates on rotation invariant systems, for instance, and that's fine. In particular, I've showed that we can have a fourfold rotation symmetry on a hexagonal lattice. We can have continuous rotation symmetry on an irregular lattice, and we can have Poincare invariance on a square lattice. These are all absolutely fine. All right, I'll close this section of the talk off here, and then I'll talk about some questions that this raises for me, and hopefully questions this raises for you as well.